Hello.
Hello? Sir?
Audible.
Yes, sir. Audible, sir.
Okay, okay. Thank you. So, yesterday we were dealing the Henry Law. I think Henry Law is quite okay for you. You understood
Sir.
the Henry Law? Hello.
Yes, sir.
Okay. Just I am finding the this one whiteboard. New whiteboard. So, what is the application? Can I ask the application of Henry Law? Any idea about the application of Henry Law? Where do we apply the Henry
Sir,
Law?
for storing carbonated drinks.
Okay, okay, okay. Storing the carbonated drink is the correct one. If I will ask you, that is, what condition will you apply while storing the carbonated drink?
Sir, it should be under
Mm-hmm.
high pressure
Uh-huh.
and should be lower in temperature so that the high amount of carbon dioxide is able to dissolve in the liquid.
Mm-hmm. Mm-hmm. Okay,
Because,
correct, correct. Mm-hmm.
yes, sir,
Mm-hmm.
solubility is directly proportional, inversely proportional to temperature and
Uh-huh.
directly proportional to pressure.
Okay, great, great. Acha, one more thing. What will be the graph of the Henry law? What will be the graph? Suppose in term of the partial pressure you are putting, here is partial pressure and here you are putting the mole fraction. Let us have a look partial pressure of CO2. You can take the CO2 and here is mole fraction of CO2. How will be the graph looking like? What do you think? Where will be the slope? Just I want to know slope. Like P,
Yes, sir.
P is equal to what is there? KHX. Huh. So Y is equal to mx plus c, right? So KH, this is the M is representing the slope, right? And on a
Yes, sir.
x-axis, this is mole fraction. This is there. On this is the x-axis. So x-axis you are taking the that is what mole fraction, mole fraction. And what the other that is the y-axis that is partial pressure. So this slope is what? That is the positive slope, na? So that is what is slope. If you are writing
Yes, sir.
slope, this is the going to be kh. Okay, this is. So graph of the Henry law will be like this. Now come back to the another one, solubility of solid and this one. Just a second.
Sir,
Solid.
once again, once.
Uh,
Yes, sir. Continue, sir.
okay. So handwriting will be little bit difficult now because I'm writing on the pen tab.
Ah,
Okay.
yes, sir.
Uh,
I understand, sir. I understand
uh,
that already.
Writing in the tab, this is very smooth and this is not very rough one. So solubility of liquid solution. It is a study in the term of vapor pressure. Vapor pressure. Right. This is a study in the term of vapor pressure and mole fraction. Mole fraction. And if you talk about the gas in liquid, it is study in the term of partial pressure and mole fraction. Here it is being studied in the term of vapor pressure and mole fraction. If I will ask you, what do you mean by vapor pressure? Can you define vapor pressure? Can you give
So
me any idea? Vapor pressure. Just give me little idea. Huh. Yes.
the pressure of a
Mhm.
partial pressure of a liquid in vapor form.
Partial pressure of liquid in the vapor form. Okay. Any other definition apart from this? It is somewhat correct only. Mhm.
No, sir.
Okay. So vapor pressure is what that is. Partial pressure, we don't use the term here because it is not the gas. Gas in liquid, that is partial pressure. So what is vapor pressure? This is the pressure, what the time pressure exerted by, exerted. This is EXE, exerted by vapors of liquid, vapors of liquid, vapors of liquid over liquid surface, over liquid surface, over liquid surface.
Yes, sir.
Huh. So vapors of liquid over the liquid surface. For example, if you want to know, this is suppose the liquid will be there. That too we have to study in
Uh-huh.
the closed container because it is the vapor. And here these are the liquid solution are there. So at particular temperature, this will be the vapor is going to form. These are the vapors. So what the point they are talking that on this no surface of the liquid, how much this pressure is going to be applied by the vapors of this liquid. So that is what the pressure above the liquid surface by the vapor of liquid is called vapor pressure. Okay. Or another definition is also there. Okay. Pressure. They are saying pressure exerted against, against what? This is against atmospheric pressure. Atmospheric pressure. This is atmospheric pressure.
Yes, sir.
Atmospheric pressure is called vapor pressure. Is called vapor pressure. This is so this one the downward. This is used for the like the anything are evaporating now, like the sea water is evaporating somewhat, river water evaporating, or whatever the pond is there, they are evaporating. For them we use
Yes,
the
sir.
vapor pressure in term of pressure exerted against the atmospheric pressure is called vapor pressure. And in our syllabus this concept is there, that is pressure exerted by vapors of liquid over liquid surface is vapor pressure. Now what do you mean by this term actually? What do you mean by this term? Let me take the new page. Stick. Here is the clear page. Okay. Now, see, we are talking about liquid solution, liquid solution. In term of vapor pressure proportional to, they are talking about mole fraction. These two term we are studying. So, how the solubility? So, we study according to Raoults law, Raults, Raoults law. Can you define this Raoults law for liquid
Uh,
solution? Huh. Just almost you gave the correct answer only. Just you need to tell only so that we can you
yeah.
can distinguish. Huh.
Partial vapor pressure of
Hmm.
each component in an ideal liquid solution
Hmm.
is equal to the vapor pressure of the pure component multiplied by its mole fraction.
Okay. Good. Correct. You are telling the expression actually. So this is they are saying vapor pressure of they are talking about vapor pressure of volatile liquid या volatile component see volatile components are proportional to proportional to proportional to mole fraction of the component in the solution of the component in the solution component in the solution. It is the handwriting is very poor, what to do. uh Wait, now what I can do. Yes. Actually, if I am using that na, so what the sound problem creating yesterday one. So that is why I am using this one, but the handwriting is may not be clear. So they are saying vapor pressure of volatile component are proportional to mole fraction of the component in the solution. What do you mean by this? suppose vapor pressure P. The two component you are having. What are the two component? Suppose one component is solute and another component is solvent. So here is solute. If you talk about that is component is 2, and solvent, whenever you are talking solvent, it can be component 1. So if you are saying this one, so vapor pressure, this is P1.
Sir, one second, sir. One second.
Huh?
Hello.
Yes. Audible? Hello.
Sir, one second, sir.
No problem, no problem.
Sir, please
Uh,
continue, sir.
okay. So here they are saying the vapor pressure is proportional to mole fraction of the volatile component. Here you can define this one. What they are saying, vapor pressure of volatile component. Volatile component means liquid components are proportional to mole fraction of the component in the solution. Okay, in the solution. Now, so one is the firstly secondary condition is the solute. Whatever two we are writing, that is solute, and that is one, that is we write the solvent. So what will be there? Vapor pressure means the pressure, partial pressure also you can say. So P1 proportional to X1 and P2 proportional to X2. Now what you need to do? We need to remove the proportionality constant. So while removing the proportionality constant, it will come P1 not X1, and this is going to be P2 not X2. Can you understand this?
Yes, sir.
Okay. So now what we can do for the solution, total pressure we need to calculate. So total pressure, to calculate the total pressure, I need to take the fresh page here. Uh, okay, new page. That page. Just a second. Huh. So total pressure, what will be there? P total, if you are calculating P total, so it is going to be P1 plus P2, right? P1 plus P2. So P1
Yes,
plus
sir.
P2, this is P1 is the vapor pressure of the solvent, P2 is vapor pressure of the solute. So it will be there P1 is equal to P1 not X1 plus it is going to be P2 not X2. See, you need to calculate the mole fraction of solute. One thing you need to keep in mind. And one thing, what is the sum of mole fraction? X1 plus X2, what will be? How much it
One,
value will
sir.
be? It is 1.
One.
Thank you very much. Okay. So X1 is equal to what will be there? 1 minus X2. So we are going to plug this value at this place. So PT, if you are calculating P total, so let me there P1 not in bracket. This is 1 minus X2 plus this is going to be P2 not X2. This is one bracket, one formula you can also use this one. Okay. But the vapor pressure of the solution is related to Mole fraction of any one component. That is also correct. So
Yes, sir.
you can multiply this one, P total. This is P total. If you are multiplying, so what is there? This is going P1 naught minus, this is P1 naught x2 plus here is P2 naught x2. So one thing you can get, the positive term we need to take the beginning. So this is P1 naught, my here will be plus positive term I am taking the first. P2 naught x2 minus P1 naught, it is going to be P1 naught, and what it will be uh, x2. What is the common in this term? Can you tell me the common? P1 naught is as it is single term, there is nothing to
Yes, sir.
say common here. Here is there x2 and x2 are common. So this we are taking
Yes,
x2.
sir.
In bracket, it is
Yes, sir.
going to be P2 naught minus, this is going to be P1 naught. This is the mode. So according to this concept, this equation, so total pressure is related to mole fraction of solute. Total vapor pressure, can you see? Because what is there? Mole fraction of only one component is there, na? Solute is there, not any other component. Yes, yeah, no.
Yes, sir.
So that is what the this Raoults law is saying. P total, P total, P total can be related to mole fraction of solute. Mole fraction of solute. What do you mean by mole fraction of solute? What do you mean by this one? If the mole fraction is more, mole fraction is more, so vapor pressure is going to be more. As much as you are adding the volatile component, liquid component, vapor pressure will be high, high and high. So this is what. So if you are going to be asked, the what do you mean by P1 in this equation? P1. So this is the vapor pressure of solvent, vapor pressure of solvent, and that solvent should be pure. This is the pure. P1 naught is there. So P1 naught. What is the P2 naught? P2 naught, vapor pressure of solute, and that what will be the solute? That is pure. It should be pure. PT. What do you mean by PT? So that is the total pressure of solution. Total pressure of solution. Total pressure of solution. Now, what we can do, we can solve some of the problem. Okay. Other classes, how you are attempting like the you are Zoom or some other source you people are using?
Sir,
Mm-hmm.
Teams we use.
At a team, na? Okay, okay. One second. Now, let us have. Do you have the book here? Book with you? Do you have the book?
Yes, sir. Yes, sir.
Okay, NCRT book. Firstly, you solve the.
Yes,
Acha,
sir.
I'm erasing this now. I'm erasing. Can I erase this?
Yes, sir. Yes, sir.
Okay. Now one more page here we are adding. What the page other mole fraction in vapor phase. Mole fraction in vapor phase. This is also mole fraction in vapor phase. What do you mean by vapor phase? Vapor phase means when the component are in the gas phase. Total component in the gas phase. So mole fraction in gas phase is represented by Y. Here they are saying mole fraction in gas phase is represented by Y, not S, X, represented by Y. That we need to keep in mind. And how to we calculate? How to calculate? So P1 is equal to P total, this is P total Y1. P1 is equal to P total Y1. This is. So a P total, this we can get from where? That is from Raoults law. P total you can get from Raoults law. Raoults. Raoults law. What is the P total? PT is equal to P1 naught x1 plus P2 naught x2 from this equation. P1, how to calculate? This is the vapor pressure. So vapor pressure you can calculate P1 is equal to P1 naught x1, this formula. So if anybody is asking what is the mole fraction of the component 1 in the gas phase, so you can divide P1 by P total. This is. And if they are asking P2, so this will be Y2 mole fraction of second component solute. It will be P2 by P total. So this way we calculate the vapor pressure, that is mole fraction in the vapor phase. So mole fraction in the vapor phase to calculate, that is you should know the partial pressure of the one component along with the total pressure. So you can get the mole fraction in the gas phase or the vapor phase. So let us have a look over the problem. So problem is example 1.5. If you see example,
Before solving problems, can we finish qualitative properties?
yes, we can. Acha, before
So
going
this,
calling,
I need to complete fast, sir, because we need revision on the next exam as well.
okay, sure. Okay, before that, na, you should know that is the ideal and non-ideal solution. Just you quick revise ideal and non-ideal. You tell that I will go the colligative. Before that, can you tell me what is ideal and what is non-ideal?
Sir, ideal solutions are the solutions that follow Raoults law,
Uh-huh.
and they are
Mm-hmm.
their enthalpy change of heat and volume are zero,
Mm-hmm.
and
Uh-huh. Uh-huh.
there if a solution is made from solution A and B,
Okay.
then
Mm-hmm.
the interaction between A B particles are similar or equal to A particles and AB particle interactions.
Okay. Great. Okay. And non-ideal, that will be going to be a reverse one. That is, they do
Yes, sir.
not follow the Raoult's law over entire range of concentration. That you need to use the term entire range of concentration. Here, enthalpy can
Yes,
be
sir.
greater or less than zero, and volume either it is going to increase or going to decrease. That is very much correct. Okay. Now, what is the positive and negative deviation? Just you give me positive deviation, because this is based on the Raoult's law, and negative deviation. So if I will ask you
Yes,
positive deviation from Raoult's law,
sir.
listen.
AB interactions are
Mhm.
weaker than AA and BP interactions, then we get
Mhm.
positive deviation. If the
Okay.
AB interactions are stronger than AA and BP interactions, then it will be
Huh.
negative deviation.
Okay. Great. Okay, so I'm not asking the explanation from you, examples also. You know very well. Acha, maximum, yeah, minimum. This is minimum boiling azeotrope. Minimum boiling azeotrope. Boiling azeotrope. What is actually azeotrope? Azeotrope.
Um,
Huh. And
Zero,
mhm.
what's it?
Maximum boiling azeotrope. This is also the related to a non-ideal solution. Maximum boiling azeotrope.
Yes, sir.
Azeotrope. So azeotropes are the mixture. Okay, this is the mixture of non-ideal solution. They are saying non-ideal solution. That is why the term
Yes,
minimum
sir.
and maximum use. Non-ideal solution. They are talking about the mixture of non-ideal solution having composition, having same composition. You can say same composition. Where is going to be same composition? Same composition. That is in
Yes.
gas phase, gas phase, and aqueous phase, and aqueous phase, aqueous phase. So this is going to be the what? Azeotropic mixture. So those mixture which have same composition in gas phase along with the vapor phase, that is what is called basiotropic mixture. These mixture cannot be separated by, cannot be separated by. You cannot separate this one? Cannot be separated by distillation, simple distillation, distillation. Why they cannot be separated by simple distillation? Because they are saying what? Same composition, that is cannot be separated by simple distillation, as they boil at boil at same temperature means both the component is going to be boil at the same temperature. Are you getting this one? Same temperature, that is why the going to be same composition now. When can be same composition in vapor phase? When both our component are getting boiled at the same time. Are you getting this?
Yes, sir.
Okay. Now, how can you say minimum boiling? If you define the minimum boiling azeotrope, this is boil at low temperature. Boil at low temperature. This is going to be boil at low temperature, and this is going to be boil at high temperature. What high temperature? What do you mean by this term actually? If you see this term, just you see 1 second. Huh. Boil at low temperature or boil at high temperature, what is meaning? If anybody is asked to explain the meaning. So let us have a look over it. Azeotrope, AZEO, little bit time it is taking now. Azeotrope. So one is the minimum. Another is what is their maximum. What I use the term, this one minimum, boil at low temperature. Acha, tell me, if anything is boiling at low temperature, so it is vaporizing easily or vaporizing with difficulty?
Very easily.
Easily. So if vaporizing easily vaporize. If it is easily vaporize, it means high vapor pressure. Yes or no?
Yes,
If anything easily
yes,
vapor,
sir.
high vapor pressure means positive deviation or negative deviation. High vapor means positive or negative.
The positive, I think.
Positive deviation. Positive deviation. So solution showing positive deviation from minimum boiling azeotrope. Are you getting this? Minimum boiling
Yes,
azeotrope.
sir.
Huh. And if you talk about maximum boiling azeotrope, boil at high temperature. Boil at high temperature. High temperature, if it is boiling at high temperature, so this is not going to easily vaporize. Means it is low vapor pressure. Low vapor pressure means what? That is negative deviation. The solution showing negative deviation from the Raoult's law is representing the maximum boiling azeotrope. Are you getting?
Yes, sir.
Okay. Acha, one last point. You tell me Pt greater than P1 not x1 plus P2 not x2. And another is there P total is less than P1 not x1 plus P2 not x2. Which is the case of positive deviation? Which is case of negative deviation out of these two? Which is
Sir,
positive? Hmm.
for left one, with which PT is higher,
Hmm.
there will be a negative deviation.
Why?
And
Vapor pressure high. See, vapor pressure high. Just now you said, na,
oh,
AB is
paper
going.
weight is high.
Ah, that is P total is high, na? P total high means total pressure high. So why it is
Ah,
coming? Why? Because of weak interaction is there. Weak interaction means all the
okay,
molecule escaping. So all the molecule
okay, sir.
escaping. So P total high. So that is going to be positive deviation. Positive deviation. Okay. Another you see, this is the vapor pressure. Total pressure is less when coming when the interaction is very strong. A strong interaction means they are not going to vaporize. Low vapor pressure, so that is going to be negative deviation. This is going to be negative deviation. So minimum boiling azeotrope boil at low temperature, easily vaporize, that is high vapor pressure, shown by what? Positive deviation. So here is positive coming now when this interaction AB interaction is weak, means all the molecule escape, means more vapor pressure, that is positive deviation. Are you getting this?
Yes, sir, understood.
Okay. Now come back to the colligative properties, what you are asking that one. Okay. Can you define what is the colligative properties? Just in one line. Anything you know about colligative properties, that you tell me. What do you mean by colligative properties? Hmm. Acha. I am telling you na. So they are saying those properties which depends upon number of number of solute particle only, number of solute particles only, and not on their nature, and not on their nature, is known as colligative properties, is known as colligative properties, colligative properties. So what do you mean by this one? what do- so they are not talking about the that is volatile, non-volatile. They are not concerned about the colligative properties. They are only concerned about the number of solute particle. You can see here, this is the number of solute particle. Very easily you can understand. So they are saying those properties, whatever it may be, which depends upon what number of solute particles only and not on their nature is known as colligative properties. Can you understand this point?
Yes,
So
sir.
colligative properties, if you are talking about colligative properties, whatever colligative properties will be proportional to number of solute particle only, number of solute particles, number of solute
Hmm.
particle. That you remember this one. So those properties which depends on number of solute particles are known as colligative properties. Now if I will ask you, what are the type of colligative properties? Have you heard about the type of colligative properties?
Yes, sir.
Mm-hmm.
Depression in freezing point,
Okay.
compression and boiling point, increase in boiling point,
Okay, okay, great.
osmotic pressure.
हाँ. Total in our syllabus only four types are there. Other colligative
Yes,
properties
sir.
are also there. So first properties, if you talk about, so let us have a depression in freezing, depression, not elevation in boiling point. The first one you study, elevation in boiling point, elevation in boiling point. This is elevation in boiling point.
Hmm.
Second one, depression in freezing point, depression in freezing point,
Yes, sir.
freezing point. These all can be correlated. There is no problem in it. RLBP, relative lowering vapor pressure, relative lowering vapor pressure, vapor pressure. And the last one is osmotic pressure, OSMOTIC, osmotic pressure. See, after that, no want of factor is there. These all the properties related with the want of factor. Want of factor. So, firstly, these colligative properties is given for what is for non-ionic. They are saying for non-electrolyte. Keep in mind, non-electrolyte. These colligative properties
Sir.
initially explain for non-electrolyte. Non-electrolyte means they are not going to ionize. One thing, if you take the electrolyte, na, the number of ion, like NaCl, you take one molecule. Just you put in the water, it become Na plus Cl minus two molecule. So colligative properties will change, na. So because
Sir.
number of particles should not change. So elevation in boiling point, depression in freezing point, relative lowering vapor pressure, osmotic pressure, these are the colligative properties. Now let us have a look over the first colligative properties. Elevation in boiling point. What is meaning of elevation in boiling point?
Hmm.
Elevation in boiling point. This is very simple. Boiling point. They are saying when, here you see, I am writing the statement when non-volatile. What you are adding? Non-volatile. If you add the that is volatile, that will become liquid. Now, liquid solution, then it will apply the Raoult's law. Okay. But here we are not using liquid. We are using the solid in liquid. So here the term, see the term when non-volatile, this is non-volatile, volatile, solute is added to pure solvent. This is the pure solvent. Then vapor pressure of pressure of vapor pressure of vapor pressure, don't write vapor pressure here, simply
Will
write then.
decrease.
Yes, vapor pressure decrease, but boiling point, what will happen? The boiling point, then boiling point of boiling point of solution increases, boiling point of solution increases increases from pure solvent, pure solvent, pure solvent is called, they are talking, is called elevation in boiling point, elevation in boiling point, elevation in boiling point. See, if the Zoom meeting is the purchase one, license one, so it run very smoothly and it never distract the volume and anything. But it is the not the purchase one, so it create the problem sometime, right? So here they are saying that is when non-volatile solute is added to pure solvent, then boiling point of solution 730. Boiling point of solution increases 630, 630, 630, 630. Then increases from mole pure solvent is called elevation in boiling point. What is meaning of this actually? If you try to understand here, so two things we are taking here. So pure solvent here is what is there? Pure solvent. This is pure solvent. Here is pure solvent. So pure solvent, all are liquid, na? So all are liquid, total surface, whatever the surface particle are there, they are going to vaporize. So if they are going to vaporize, so it is going to be high vapor pressure. High vapor pressure. Now come back to the you if you added here what solid solute. So solid do not having the vapor pressure, na? Solid do not having vapor pressure. So what will be
Yes.
having whatever the liquid are there, na? And here the solid particle will also be because it is the solution. So solid particles are also there. So surface area for the liquid solution is decreased. Okay. So vapor pressure also decrease. What you use the word? Now, if the vapor pressure decrease, so what will happen? The vapor pressure here will be low vapor pressure. Low LOW. Low vapor pressure of solution. Solution vapor pressure will be what? Low. But pure solvent vapor pressure will be high. Can you be able to understand?
Yes, sir.
Huh. Why vapor pressure is low? Because this solid particle is occupying the surface, na? Surface air. So that is why. Now one thing you should know, like we are boiling the water, that is pure water. You add the salt in it or the rice in it, sugar in it, wheat in it, whatever, the boiling is stopped. Suddenly boiling will be stopped. Why? Because vapor pressure decrease. To boil the solution now, both the component, you need to heat more. So that is what they are talking about. So boiling point, increase in boiling point is represented by delta TB. This is the this
Yes, sir.
delta TB is elevation in boiling point. Elevation in boiling point. This is elevation in boiling point. Now another
Yes, sir.
term you should know another term. What the other term you can need elevation in boiling point means that is which boiling point is more. So that is TB minus TB naught. TB naught means this is boiling point of
Yes, sir.
pure solvent like 100 degree. Water boil at 100 degree, but water and salt that boil at higher temperature. So this is going to be BP of what? Solution. BP of solution. This is SOLUTION. BP of solution. Now another term you see, I am taking another page. So they are saying elevation in boiling point is proportional to, can you tell me? Elevation in boiling point, elevation in boiling point is proportional to, proportional to molality, MOLALITY. So they are talking about delta TB proportional to small m. This is the molality, MOLALITY. So delta TB, if you are writing equal to KB multiply by m. So now delta TB already I defined you na, TB minus TB naught is equal to KB molality. So moles of solute, it will be moles of solute, moles of solute divided by mass of solvent in kg, mass of solvent in kg, in kg. So here you see, uh, so small m is equal to moles, W2 by M2 divided by W1, and that will be the divided in kg, that is 1000. So it delta TB is equal to, this is KB multiply by W2 multiply by 1000 divided by what will be there, M2 W multiply that will be M2 and W1. This one. Can you understand this? What is W1?
Yes, sir.
W2. W2 gram mass of what? Solute. Gram mass of solute. M2 molar mass. Molar mass of solute. Molar mass of solute. W1 gram mass of solvent. Gram mass of solvent. This is gram mass of solvent. Now they are saying Kb. Kb is called ebullioscopic constant. Ebullioscopic. Scopic. Ebullioscopic constant. Okay, that is also called molar elevation constant. Ebullioscopic constant is also called molar elevation constant. So we got the formula delta TB is equal to Kb into W2 multiply by 1000 divided by M2 into W1.